Let's talk about truth tables for conditional and biconditional. This joins with our truth tables for negation, conjunction, and disjunction that we talked about in the previous section. Before we go into these truth tables, there's two logical definitions that we have. One is the phrase tautology. It's a compound statement that's always true. So sometimes you might say to somebody after they've talked for a long time, what you said is a tautology. And that just means that they've said something that's always true. In general, things that are always true are fairly useless. Self-contradictions, on the other hand, are compound statements that are always false. If somebody says something that's self-contradictory, they've created something that's invariably false. So let's talk about conditional and biconditional, and then we'll analyze this rather large-looking truth table here at the bottom. First, the conditional, if P, then Q. How does this statement end up being true? Well, it can be true in one way that seems obvious. If P is true, then Q is true, and that makes the whole statement true. And this is the format we're usually used to. If you get a 90% or higher in the class, then you'll get an A in the class. If this is true, then this is true. That makes the whole statement true. So I can say that as long as you get a 90% or higher and then I give you that A at the end of semester, then you know I said a true statement. However, there's two other ways that the if-then statement can come out to be true. So let's talk about those first. So let's skip over this one. If I tell you that if I give you a 90%, if you earn a 90% or higher in the class, then you get an A in the class, and suppose you don't earn a 90% or higher, but you still get an A. This is the case where you get an 89.49. I said I would round that up to 89.5, which would round up to 90%. So even though you didn't get the 90 or higher, you still got your A. That getting the A part was true. My statement still stays true. The overall statement, if you get a 90% or higher, then you get an A, it's true. Why? Because nothing broke it. Statements and these compound statements become true as long as nobody's lied. I'm free to give you an A even if you don't get a 90%, provided you got really, really close, like an 89.5. On the other hand, suppose you don't get a 90%. Suppose you get lower than a 90%, and I don't give you an A. Well, then my statement is still true because all I did was promise you under my grading scale on the syllabus that if you get a 90% or higher, then you will get an A. And so if you don't get a 90% or higher, I'm perfectly fine giving you a B. That's acceptable. It still makes my statement true. I haven't lied. So the statement here, the if P then Q statement, it only becomes false if you do your part and I don't do mine. You went and studied hard, you hit the books, you practiced, you watched the videos, you went on and did the textbook examples all out and worked hours and hours and hours, and you got yourself a 92%, and so this part was true, and then I don't give you an A. That's the only time when I've lied, and that's the only time when this statement would be false. It's the same logic that tells me how the biconditional truth table is going to go. If this is true, this is true if P, then Q, because remember the biconditional first has an arrow going to the right. You can ignore this part right here and just focus in on this part of the biconditional for a second. Well, true, true tells me this is going to be true. And then if I look down here, false, true, well, that tells me this will give me out a false statement here. And if I look at this false, false, again, if the left side is false and the right side is false, that makes the whole thing true. The biconditional is going to be true when both of these match, because really what this biconditional, this if and only if means is it says the left side is basically the same thing as the right side. So if they're both true, well, that means that the balance of my statement, the left side was the right side. They were both true. If they're both false, well, once again, the left side was false, the right side was false. That makes my biconditional statement true. The only way it can be false is if the two sides are unequal with this false, false, and true, false. Now that we're in section 3.4 and we've got these truth tables for conditional and biconditional, these truth tables right here are the ones you want to have memorized. If you know these truth tables, you can build up everything else. The last section in this chapter 3 that we're going to go to, 3.5, all it's going to do is give us some words for some special things, special cases that involve all these different connectors. So these are the tables you want to know and memorize. If you can do that, then you can do any sort of truth table. So let's build up this truth table. I've got the statement here on the far right. This is what I'm after. I've got the statement that Q implies not R and not R implies P if and only if Q and not P. That's my statement I'm after. I'm going to break it into chunks. I'm first going to understand what this statement means. Q implies not R. To make that happen, I'm going to have to get all sorts of things into play here. And since I have a not R and I have not P, I'm going to have to add myself 2 columns into here. One of my columns is going to give me not R, and one of my columns is going to give me not P. All right. So let's take all these and let's go through and figure out what have we got going here and what is my final set of information. And if this full column, all this column here on the far right, if all of these possibilities are all trues, then this would be a tautological statement. If they're all falses, this would be a self-contradiction statement. So let's talk. Not P. It's going to be false, 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 and then true, 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 true. Not R is going to be false, true, false, true, false, true, false, true. Take a second and make sure and convince yourself that I've done the right not P's and not R's. So now let's talk. Q implies not R. Let's focus in on this implies part. This implies here is my conditional. Conditional statements are usually true. The only time conditional statements are false is when the left side's true and the right side's false. So that means that we want to focus in on something. In general, if the right side, if this Q is true, I know right away that my statement is true. So every place where R is true, not R is true, I know this guy is going to be true. So I've got that out of the way. Now I have to look. See, if Q is true, it was true. Q is true, this was true. So now I have to focus in on these false parts. If the not R is false, because I'm after this not R, now I have to look at the first part. If the first part is true, that's the only time this is going to be false. So not R is false. Let's look at Q. It was true. That makes this whole thing false. Because I had true implies false. The precondition, the antecedent, was met and successfully implemented, and I didn't give you the consequence. So that makes the statement false. Here I've got my consequence being false. Let's go back and look at my antecedent. My antecedent was false. This is perfectly fine. False, false gives me a true. All right, go back and look at Q. My Q is true. You gave me the antecedent. I didn't give you the consequence. This is false. And finally, over here, Q is false. As soon as Q is false, as soon as the first thing's false, it doesn't matter what happens at the second part. Either way, this guy's going to be true. So I've got my Q implies not R. All right, now let's look at not R implies P. Again, as long as the second part is true, we know the whole statement will be true. So let's look at P. P is the second part here in this statement. Not R implies P. So I've got true, 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 true here. Every time the second piece was true, we're doubling up on what P's and Q's mean and who's first and who's second. Focus on antecedent and consequence. If your consequence, which is the second part here, if your consequence is true, your outcome for the whole statement is true. So here my consequence is P. P's true in all these places, so that gets me true down the board here. Now I have to look at the next part. When my consequence is false, my statement's only going to be false when my antecedent is true. So this is all the places where P is false. I'm looking for the places to get the rest of my true statements where my antecedent is also false. My antecedent is not R, so if I see a not R being false, then the whole thing's true. If I see a not R being false, then the whole thing's true. It's only these remaining places that are going to be false. Now I've got and. It's and that's joining this statement and this statement. Remember how and works. Both of them have to be true for the and statement to be true. So I've got one of these guys false. That doesn't work. Let's go through and do all the true first. I've got double trues, double trues, double trues, double trues. Everybody else is going to be false. Now I go down here onto this far side. I grab this last piece right here, this Q and not P. Again, and is only going to hold true when both the left and the right sides are true statements. So I've got Q and not P. So I'm looking in this Q column and I'm looking in this not P column. Again, I'm going to go through and talk about trues first. I've got true and false, so that's no good. I've got true and false, so that's no good. I've got false and false, that's no good. False and false, that's no good. Here's true and true, that gives me true. Here's another true and true, that gives me true. Over here I've got falses again. So when I had Q and not P, another way to look at this, when I have not P, if one side of an and statement's false, for not P, these first four ones are all false for sure. It's only these latter two that have a chance. This is where the not P is true. So then I go over here and look at Q. And I've got trues and trues, so I've got those true options, but here I've got the falses, so these have to be false. Now for my final thing that I'm looking at, I'm trying to look for this biconditional here and see what's going on. How's the biconditional work? If the left side and the right side of a biconditional match, I get true. If the left side and the right side of a biconditional match, I get true. Doesn't matter if they're matching at trues or falses. This is different, notice, than and, where you have to have them matching trues to get trues, but if they're matching falses, the whole thing's still false. Got the left two matching, no matter whether it's true and false matching. If they're matching, you get yourselves true. So as I go down this row, I'm just seeing if these two match. So I've got a double F, which makes it true. Got a double F, which makes it true. Here I've got true and false. There's this mismatch, so it's false. There's a mismatch. Mismatch. So this statement at the end of the day, sometimes he's true, sometimes he's false. More false than true in general. That means it's not a tautology, it's not a self-contradiction. This is just your normal, straight-up compound statement. It's got some true cases, it's got some not true statements, depending on what's happening here. So this far column down here is my final answer for this. Some things I want you to do is to go and look at the examples for the section, make sure you work through those, and then we're going to break into section 3.5 where I start giving some logic names to some of these truth table situations that we can find, and we'll find things that are equivalent, different ways of saying the same thing.